My name is Shannon Copeland from Belton High School, and today I'll be explaining a topic in math that has applications in almost every field, from biology and geography to image compressing and computer graphics: fractals.
What exactly is a fractal? A fractal is defined as a geometric shape which is both self-similar and has fractional dimension. Now what does that mean? In general, a fractal is any geometric shape that, through a repeated pattern, looks the same or similar at smaller and smaller scales. As an example, let's turn this simple line into a fractal. First, add a triangle to the center of the segment, then add a triangle to the center of each new segment created, and again. This can be done indefinitely many times to create a fractal. Putting 3 of these segments together into a triangle creates a very well-known fractal, the Koch snowflake. Other simple fractals include the Sierpinski carpet and triangle, the dragon curve fractal, and the Cantor set. Remember the part of the definition that said fractional dimension? It's easy to picture a one-dimensional line or a two-dimensional square, but how on earth could something exist at a dimension of 1.5 or 2.7? The answer lies in fractals. Imagine we have a one-dimensional line, a two-dimensional square, and a three-dimensional cube. Now let's double their measurements, creating 2 self-similar lines, 4 self-similar squares, and 8 self-similar cubes. But hang on, aren't these self-similarity values all powers of 2? As it turns out, the dimension of a given geometric figure can be defined by n equals r to the d, where n is the number of self-similar sections, r is the magnification factor, in this case 2, and d is the value of the dimension. Finding the dimension of a figure in terms of n is derived from that. D equals log of n over log of r. Now, let's try this formula on our Sierpinski triangle. Let's use 2 again for the magnification factor, r. Now we need n, the number of self-similar sections. The Sierpinski triangle has 3 sections that are self-similar. So to calculate dimension, we take log of 3 over log of 2, which approximately equals 1.58. Though we can't really visualize it, the Sierpinski triangle's dimension is fractional. As the dimension of a fractal increases, the complexity of a fractal also increases. This is all very interesting mathematically, but what uses are there for fractals besides the coolest screensavers ever? We can find fractals in the self-similarity of clouds, coastlines, lightning, lungs, and all kinds of plants. Studying fractals helps us understand why these facets of nature behave the way they do. The concepts behind fractals also have propelled incredible advancement in computing. Recursive landscape graphics in video games minimize programming time and memory usage, and fractal compression can maintain a photograph's resolution while zooming in indefinitely. This computer coolant system takes inspiration from the fractals in lungs to evenly disperse coolant, and this fractal antenna uses self-similarity to transmit and receive information over a wide range of frequencies.
Fractals are useful mathematical tools for a wide range of applications in every aspect of STEM. Complexity aside, one thing's for sure: they're more than just a screensaver. Thanks for watching.